So concavity, so this is asking for concave up, concave down, so we definitely know at this point that's our second derivative, ideally. And we can get to our second derivative here without a major problem. You take your second derivative, and then we're looking to see, is that undefined anywhere? And it's not. We also then take that, set it equal to 0. And then what you're going to notice, and you'll know depending on which day you are on, all the ones tomorrow should factor nicely, because I would expect tomorrow to be done without a calculator. If it doesn't factor nicely like this one doesn't, then this is going to be on the second day. So this is one then that you can't do by hand, that you would now have to graph, and then on the calculator find your 0. We're not going to go through all that. We've done these plenty of times. If we were to graph it, it probably looks something kind of like this. That would be our second derivative graph. And then what you would just have to understand, I don't ask for it, but this here is our point of inflection, since that's where the second derivative is equal to 0 and it changes signs. And then concave up is when your second derivative is positive. So if I want to know when is my second derivative positive, it's going to be this whole interval here, because that's when the second derivative graph is above the x-axis. So whatever the calculator gives you as a 0, you have the answers anyway. They're online. You can do that. If I want concave down, that's when the second derivative is negative. So that's going to be anytime the second derivative graph is underneath the x-axis. So it's completely dependent upon what graph you are looking at. You're going to get a lot of graphs tomorrow, a lot of tables, and you have to just sort of understand the second derivative, first derivative, functional values. Each of those you have to interpret a little bit differently. Since that's our second derivative graph, if it's underneath the x-axis, you're concave down. If you're above the x-axis, you're going to be concave up. Okay? So the key is finding that 0. I'm going to leave that to you. You have the 0. You have the answers. We're going to move on to number 9, save a little bit of time here. Number 9, pay attention to this. This is not a misprint. Number 9 is me kind of setting up number 10. 10 is the big one, something long-term that we want to understand. Number 9, I give you a pretty simple little function, and I'm asking you this question. Where is f prime increasing? So we've done a lot of where is f increasing. I'm now asking you, where is f prime increasing? So what you want to understand, anything increases, I'll write it down. So anything increases when its derivative is positive. So if I want to know this question, if I want to know when f prime is increasing, let's first get to f prime. So there's f prime. If I want to know when f prime is increasing, it would be when f prime's derivative is positive. All right. So this really means I want f prime's derivative first, which is now actually going to be our second derivative. That's what we're going to set equal to a 0. And then that's what we're now going to be testing. The second derivative gives us the rate of change of the first derivative. All right, so we want to understand second derivative is the rate of change of the first. So if I now test this, if I take a negative value, plug it in here, 12 times a negative number is going to be negative, 12 times a positive number is going to be positive. F prime would be increasing, starting at 0 and then going to infinity. Where this will really pop up long term as we start building and pulling things together more than we already do, it'll look like number 10. When the question is now asking, you're given a position function, so this is our position, but I'm now asking you, when is the velocity decreasing? So we actually had talked about this earlier in the year, and we just memorized our velocity is decreasing when the acceleration is a negative, but we can now apply this idea here, right? Anything will increase or decrease based upon its derivative. Yeah.
I don't think we have a.
Don't have?
Number 15.
Oh, is it? Oh, go to number 16. Sorry. Really?
Yeah.
That's weird. I got so many versions of these different things that I've changed over the years, and then making copies ahead of time, I just copy the different version. We've been good up until this point. All right, that's weird. Aaron, you want to do me a solid? Grab a packet out of the envelopes up there so I know which ones are which. So we're looking at 16, supposedly. Or just bring me a packet and I'll grab it. Yeah. Thank you.
Yep.
All right, so if our velocity is decreasing, let's first get our velocity. And the velocity is the first derivative. And if that's then what we're trying to figure out where that is decreasing, then it would be when the velocity's derivative is negative. Okay, so if I want my velocity to decrease, I would want the velocity's derivative to be negative. Well, the velocity's derivative is actually our second derivative. And this should have been x plus 24. So that's what we're going to use to get our test points. This factors nicely. So 2 and -2 are our test points. I'm sorry, 2 and 1 are our test points. Certainly have to do this a handful of times tomorrow in terms of our sign chart. When we do this, it should go, and again, I'm going to assume we can do our sign charts pretty efficiently. It should go positive, negative, positive when we do this. So my velocity will decrease when my velocity's derivative is negative, but that's what this is. The second derivative or acceleration is my velocity's derivative. So we should be decreasing for a velocity between 1 and 2. All right. Man, I hope the key is okay on that. No, I'm a little concerned about what I gave you. Yeah.
So, talking about decreasing and increasing, do you always use brackets?
You would. As long as it's continuous on each end. Yes. Okay.
You said velocity for the second derivative?
Velocity is the first. So if we're testing the velocity, that's why we had to go to the second derivative. Okay.
Acceleration.
Acceleration is your second. All right, so these, I'm not going to have you graph these tomorrow. What I do want you to be able to do tomorrow, I think there's 2 questions on this, horizontal and vertical asymptotes. So let's make sure we can do that with these next 4 problems. That's all I'm going to have you do with 11. I don't even know what your numbers are now. Let me look through here.
Yeah.
So this is your 10s. All right, and then, okay, so we go in order from here. So the vertical asymptote is easy. Just make sure you write it correctly. It is a vertical line, so write it as such. That's x equals a number. So you say x equals a 1. The way that we calculate our horizontal asymptote is we take the original function and we just calculate the limit as we go to either a positive infinity or a negative infinity. So it's our old limit rule from the first week or 2. Since these degrees are the same, then the limit is just the coefficients of 2 over a 1. That means that's our horizontal asymptote, is the horizontal line y equals 2. So if we were going to graph it, which we won't, but it could play a role, you would understand then that we have a horizontal asymptote here in our graph, and then at 1 on the x-axis you have a vertical asymptote, and then we would just construct something from there based upon points, based upon when the derivative is positive, all that good stuff. Okay. All right, so number 12. Again, horizontal and vertical. The vertical asymptote is the line x equals 0. That's our excluded value. If we then went ahead and found the limit as x goes to infinity, similar to that last one, the degrees are the same. We have a squared on top and a squared on the bottom. So we just divide their coefficients, should give you a 1. So our horizontal asymptote is y equals 1. All right, 13. Vertical asymptote, x equals 2. That's easy. The horizontal asymptote is the limit as x goes to infinity. First time we've seen this, but if you remember, if the bigger degree is on top, which it is, we have a 2 versus a 1. What that's telling us is this limit is infinity. That tells us we don't actually level off towards any y value. The y's just get bigger and bigger and bigger and bigger. That would tell you that there isn't a horizontal asymptote. We have to get an actual number. This is actually an oblique asymptote. It's something we usually cover, but we skipped. I won't test you on an oblique asymptote, so don't be concerned about that tomorrow. So if you get anything other than a number like infinity, then you don't have a horizontal. All right. 14, the vertical asymptote is again x equals a 0. And then similar to that last one, this won't really happen to you tomorrow since we didn't really do oblique asymptotes this year. This being an infinity, you would again say there's no horizontal asymptote. There will be a horizontal asymptote tomorrow on the 2 questions that I'm asking you about. Okay. So don't worry too much about the ones that are none. These, just to kind of clarify, you really want to read carefully tomorrow to know which one I am asking about. So this one is asking, here's your function. So x cubed minus x, so pretty simple little guy there. If I ask, where does that function have a relative max? That's implying at what x coordinate? So we would just say at x equals whatever. If I ask you what is the relative max of the function, now I'm asking the maximum of the function. This is now where you're going to put at y equals whatever. So just read it carefully, know which is which. Most of the quick test tomorrow is multiple choice, and you want to be giving me the correct answer, obviously. Don't give me the x coordinate when I'm looking for the y coordinate. So with this one, we're going to take our first derivative. So that would give us what? X squared minus a 1. We'd set it equal to 0. So x minus a 1, x plus a 1 after we factor. So we're a simple little test here, negative 1 and 1. Yeah.
This is a fraction which was x cubed and x to 4.
Yeah, you have x cubed over 3 minus 3. Couldn't we rewrite this? Aren't these equivalent ways to write that? If I just pull the 3 out as a 1/3. So that if I then do the power rule, isn't 3 times 1/3 just going to give me a 1? And then they cancel. So we just get that x squared. All right, we do our sign chart, positive, negative, positive. So the answer to this one, since I'm just asking where do we get a relative max on that function, you would say at x equals a negative 1, because that's where the first derivative goes from negative to positive. The relative max, if I'm asking what is the max, now we actually need to figure out the functional value at that negative 1. So that's when you're going to be plugging in to the original function. So let your x's be a negative 1. And what we find f of negative 1 to be would be what? 1/3, negative 1/3 plus a 1. So our functional value then is 2/3. Okay.
Can we write that again?
You don't want, so 2 things. Tomorrow, so if it's multiple choice, so 2 things to that question. Tomorrow, I guarantee if this is the question, I'm only asking A or B in a particular problem. One answer is going to be a negative 1. One answer is going to be a 2/3. And you need to know which one I'm asking for, because if you think I'm asking for X and you give me the Y, it's going to be wrong. Same if it's the opposite. So that's one reason we want to know which is which. The other thing, on the AP test, on a free response question, which these very, very often are, if you write this as a point, so if you say like negative 1 2/3, or if you write f of negative 1 equals 2/3, they actually won't give you that credit because they view this as kind of a cop-out and you're not actually knowing which one they're looking for. And you're just kind of covering both ends by giving the x and the y. So they want you to be specific about which one you're given. Okay. Okay, so then the next question, different numbers, but they're the same question, right, so far? Yes. This we already know. This we should be good at. Sharp corner. Vertical tangents. And then any discontinuity. So that should be simple. There is a question that tests you on that, so please be good with that. And then this is an old AP question. Just expose you to different ways. So obviously tomorrow, I promise you there's going to be 5 or 6 questions. You're going to get asked the questions a little bit differently. You don't want to freak out. It's the same stuff that we've been doing. So this is another one. This is an old AP question. Just asked a little bit differently. So most questions we've done throughout this year, this is your next question too, right? Yes. Okay. Here's a function in its entirety. Where do you have a minimum? Where do you have a point of inflection? All of this. What you're now given is you're given the function here, but notice how it's not complete. We don't know what A is. We don't know what B is. We don't know what K is. And they're not asking you to find the minimum. They're giving you the minimum. And they're not asking you to find a point of inflection. They gave them the point of inflection. So they're actually given the answers, and using the answers, we got to work backwards to find the function. So what we want to understand then, if this is our function and we have a minimum, the only way we can have a minimum is at endpoints. That's one option. There are no endpoints in this problem. Those will be explicitly stated, so we don't have to worry about that. So the only other two places is when the first derivative is 0 or where the first derivative is undefined. So if we understand that, both of those deal with the first derivative. That means we probably want to take the first derivative. So take the derivative of that equation, 12x squared plus 2ax, and then the derivative of bx, the b just drops down because it's a constant. You're told it's a constant. And then the derivative of x would be a 1. So all we really get is plus b. So now what has to happen is one of two things. So don't write this next one down. You can, but it might get a little messy. If I plug in a -1 right now into this equation, would that make that derivative undefined right now? Does that cause any sort of an issue that would cause us to be undefined? No. So the x value of a -1 doesn't make that undefined. So the only other option then, if this doesn't set that up, is the idea that when x is a -1, so let your x's become a -1, it must be making our derivative equal a value of 0. Let me make this bigger for the old guys in the back with bad eyesight. So let all of your x's equal a -1. What we then end up with, this would just become a 12 minus a 2a plus a b. But then we're kind of stuck. There's nowhere else for us to go with that information. However, I have something else highlighted. So what they also gave them this year in this question is a point of inflection. Then you have to understand, well, the only way I'm going to get a point of inflection is when the second derivative is either 0 or undefined. So now we want to go ahead and take the second derivative. So now I need those. So here is our first derivative over here. So the second derivative should be 24x plus 2a. Same idea now. If you let x be a -2, it's not going to make that second derivative undefined. So the only other option is let your x be the -2, and it must be giving us a second derivative value of 0, because that's the only times we can get a point of inflection. And then what we get pretty quickly is a little equation there that we can solve for a. And we get a to be my personal favorite number, 24. So we have that done. And then over here, we can let a be a 24. And then that allows us to figure out what our b is. All right, so solve that, and that should give you 36. Okay. So that's an old way. They've given on free response question a way to test on all this stuff.
What about K?
K we can't do right now. So there was an extra question to this. We can't figure out K right now until we knew the antiderivative of this. So that's why in this case, I only ask you for A and B.
Oh,
Yeah, so eventually you'll know how to find K. With what you would need more information, and you would need to know how to do it because we haven't been exposed to that just yet. Okay, these I'm probably going to, at least this next one I'm probably going to leave you. We'll get it started. The idea, where is this function increasing, means we need to take the derivative of this. This is, and then I did not do that right because I'm trying to see if this is the same thing. Sine 4. Yeah, that's your next question. And then you look to see if it's undefined anywhere, and it's not. So this is a calculator question. So this is going to be on your second day. So at some point, look this over. This should look kind of like a parabola. This is y prime. You're going to be increasing when the first derivative is positive. If you are looking at the first derivative, when it's above the x-axis would be what we're looking for. Okay. But again, without our calculator, and I don't want to take the time to go through all of that, it's this interval that I have shaded in yellow on the left, and then over here on the right. Okay. These I want to do. So you do have to work with an E for one of the problems tomorrow. I just added that a short time ago to the test. So where do we have a local max or min? So extrema just means max or min, either one. And then this is our function. So without our calculator, so we're going to take our derivative. You'd have to recognize you have a product rule first. So you do 1 e to the x, and then leave the x alone, and then the derivative of the e to the x is itself. Minus, and then drop that 2 down, the derivative of e to the x is again itself. So tomorrow, when you shouldn't be having to graph anything on the calculator, that means this should factor nicely. So as we set this equal to 0, somehow that should clean up nicely. Most people don't see this right away, so they pull the e to the x out first, which is totally fine. And then you get x minus a1. So if we do it right, it should factor nicely without a calculator so that we can set up a little sign chart here. And then remember some of the things that we had talked about where this e to the x, even though it has a variable here, the exponential function can never cross the x-axis. It's always a positive value. So when we go to test this and I take a 0, 0 minus 1 would be negative. This factor here can spit out nothing other than positive numbers. So overall, that is a negative value. If we go greater than 1, let's say 2, then 2 minus 1 is also now positive. E to the x is always positive. So that's a positive. So what that allows us to now say is that we have a, not maximum, we have a minimum at x equals 1. Okay. Okay, same with 20. So now this is asking for a point of inflection. So real quick, just to make sure we remember how to do this, product rule, ease. Point of inflection, we should definitely know is a second derivative. So take the second derivative of that. Make sure we can get through those couple steps. And if you're feeling confident, factor it. We should be able to get a nice factored version to set up a nice, easy sign chart with that. All right, so the first derivative we just did in the previous problem, largely. So e to the x plus x e to the x. Then we got to do it again. So this guy would have stayed the same. And then we again do the derivative of x e to the x. Hopefully we recognize we have an e to the x in all of them. And when we pull that out, we end up with an x plus a 2. Here's where it's really important to know that e to the x is always positive, because when we now go to test this negative 2, you have to plug in a -3. And you have to understand that even though I'm plugging in a negative x into this factor, it doesn't matter. That exponential function will always spit out a positive number. And then the -3 plus a 2 is definitely negative. So overall, that interval is negative. We plug in a -1, always positive. -1 plus 2 is now positive. So this is positive. So we have a point of inflection at x equals a -2. Please test those tomorrow. So remember on that quiz, just because the second derivative equals 0 doesn't guarantee a point of inflection. A lot of you fell for that on the quiz. Don't let me fool you tomorrow again. Make sure on those questions you're testing your points, making sure that you actually get a sign change. Yes? Oh, it does say coordinates? Yeah, good call there. Yeah, thank you. See, rushing. So now we just have to take our x value, plug it in right here. So we should get -2 e to the -2. All right, yeah, thank you. Okay, so then with what time we got left, go to the second review. I think I have it out somewhere. See if these numbers are the same. Yeah. Yes. Okay, so the first one. When it says find the minimum value of f of x equals whatever on the interval 1 to 4, I am looking for the value of this function. So we are looking for the y coordinate. So don't just give me that x coordinate when we have to do these. This is kind of the classic one that we started the whole chapter off with, where we listed candidates. 2 candidates without a doubt are 1 and 4. Those are our endpoints. We then have to take our derivative. We get 3x squared minus a 6x, set that equal to 0. We can test 0 and 2. 0 we're not worried about just because it doesn't fit in the interval, but the 2 we definitely do. And then from there, no need to do a sign chart. The sign chart doesn't give us functional values at all, so it's not really productive. It's not something we need. We just take our 1, plug it in, and again, you're plugging it into this original function right here. So if you plug in a 1, we get what? 1 minus 3, so -2. If you plug in a 4, we would go 64 minus 48. Yeah, so 16. And then if we plug in a 2, we would go at what? 8 minus, so -4. 8. Yes. So again, tomorrow, when I just have a list of letters for choices and we ask this question, if I put like 2 here, -4 there, make sure you're giving me the y value because that's what this question was asking for, all right? -4. That's our largest functional value. If it's free response, you would just say the absolute min is the y value of -4. If it's multiple choice, just give me the y value. Okay. 2 is very, very similar to the one that we just did. You know how to do that? I'm going to skip it because we just did one like that. And what I mean by that is it's the same exact type of question as this one, where take your first derivative, set it equal to 0. But in this case, you're going to let it be, you're going to let x be a 2. I'm going to leave you those. You can do those. We just did one like that. Let's see here. What time we got? Let me see what else I have. I'm going to make sure we get to one. Number 6. Do this for me for number 6. A lot of these are, this whole packet is old free response questions. Cross that guy out. That'll keep you busy for a while. It's a little more involved than I need you to be concerned about. So don't waste your time on that one. Yeah, that we should be able to do. I think we're good. So let's go back. Do number 4. Do 4A. Again, this whole packet is old free response questions. Every one of these is something I've taken off of an old test over the years. This question I like. going? So A was nice. This is exactly how they gave this to them. They actually give the derivative. We're looking for any maxes or mins. Similar to what we just talked about. 3 is our only test point. If I plug in a 2, this factor is negative. E to the x is always positive, so you should add a negative here. If I plug in a 4, 4 minus 3 switches this to be a positive. So overall, we're positive. So you would just say that we have a minimum at x equals 3. Then they went to letter B, and they now want to know where are we both decreasing, which we already know. We're decreasing in this interval here. But also at the same time, are we concave up? So now they're making them go to a second derivative. So we'll take a second derivative. Product rule again. So here's our x minus 3 e to the x. So the derivative of x minus 3 is a 1. Leave the e to the x. Plus leave the x minus 3 alone. And then the derivative of e to the x is itself. Set that equal to 0. I think what most people probably do is factor here, or distribute. So we get x e to the x minus a3 e to the x. So take that e to the x in the second quantity, multiply those together. Similar to the couple problems we've already done, if I pull that e to the x out, we would get a 1 plus an x minus a 3. So we get x minus a 2. That's our test point. If you plug in a 1, 1 minus 2 is negative. If you plug in a 3, 3 minus 2 is a positive. So then we know we are concave up in this interval. And then they had to make them, or they made you think, where are they doing both? Where are we decreasing and concave up? So write that down real quick, see what you think. All right. You'll get 2 to 3, hopefully. In between there, we're both decreasing, and we are concave. Okay?
Mr. Kenya,
Yes, ma'am.
why wouldn't we use brackets?
So in terms of being concave up, that's where they don't necessarily need you or want you to be putting the bracket. They took both. If you put brackets for all those, we definitely want to close any increasing or decreasing ideas. But since it was in conjunction with the idea of concavity, that's why you wouldn't necessarily have to do that, because at 2, you're not concave up or concave down. You're changing at that point. It's your point of inflection.
So do we only use brackets when we're trying to find the answer for decreasing or increasing?
Yeah, pretty much. Yep. Yep. All right. Other than that, I don't know what else we can get done in 4 minutes quickly. Let's do this. Yeah, that might be it where we stop. Again, I wouldn't worry too much about review number 3. As I look at it, the 4.5 question will not be on tomorrow. I think I may have mentioned that yesterday. Don't worry about review number 3. So 4.4, 4.5, 4.6, that's all going to be on the second day. Just no packets 1 and 2 largely. If you had any last questions on these, since we obviously didn't get through a lot of them, just look me up tomorrow morning. Okay, I'll be there by 9:30, and then we can answer anything that you need to answer before first period. Okay? All right. That's all I got. If you already have some questions, we do have 3 minutes. So if you've already kind of looked through and you have an outstanding question we didn't get to today, feel free to hang around. If not, we'll see you tomorrow. Okay? All right. See you guys. Let's pause this.